kind of the introduction is, when you boil this all down, what does it do? Remember I said the first thing you should do is take your most complex through-hole multilayer and try to simplify it with HDI, but don't move any parts. Why would that end up being any difference? Well, remember, you move the ground plane to the surface. Okay, that saved you 2 layers. So it shows you, okay, now move the ground plane to the surface. We're going to take all the traces off the surface, and moving the ground plane, we're going to use ground flood. It can be discontinuous ground flood or a continuous ground flood, depending on your nets and things like that. Well, 30 to 40% of the big vias have now been eliminated by doing that. The second thing is, we're going to do the BGA breakout with swing vias, and they're going to be micro vias. So we're going to save 2 to 8 layers just by not getting away from the multi-layer breakout strategy to an HDA breakout strategy. And we're going to make sure we have a horizontal and vertical routing pair for HDI. That's going to allow us to have 8 times more traces on those 2 layers than the through-hole design. The second thing is, we're going to move the power planes from the center of the board up to the surface as that layer pair. We're going to make it as thin as possible so that we can do a skip via, so we can go from 1 to 3. And the reason is 1 to 2 is now 20 microns or 25 microns to 30 microns. 1 to 2 is not 300 microns or 250 microns like in your multilayer. We're down to 30 microns or 20 microns. So that gives us a lot of shared capacitance but very low inductance. So our whole power supply has gone up. But we eliminated 20 to 30% of the vias. So now when we do our routing, we're getting twice to 4 times as many routed traces on the signal layers because we're not dodging through holes anymore. So that typically saves us 4 signal layers and 2 reference layers of ground. And so the multi-layer here was 18 layers, the through hole. The HDI version is 10 layers. And so that's how you go from 18 layers to 8 layers. There's no magic. It's just taking the thing apart. And do we need that extra layer? I want a thinner board. I want fewer holes. And so the case studies will show you that typically the case study, we're taking out 10,000 drilled vias or 8,000 drilled vias. You can't imagine how much space 10,000 mechanically drilled vias occupy going all the way through the board. But you'll see it in the kind of the case study. The famous one is the one that affects all of you, and that's all of the optical networking controllers for the Boeing 787. So you better hope we're right, because this is a plastic airplane with no copper wiring in it, except the cockpit. But outside of the cockpit, everything is optical. There's no copper wiring. But there's a triple redundancy in the optical network. And so, that's a picture of the board. Interesting enough, they would never explain to me what this is. That is so proprietary, I couldn't touch it, and they wouldn't explain what it is. After several beers, I kind of found out this self-healing circuitry. In other words, this board can repair itself. Don't ask me how, but that's the circuitry that is self-repairing. And so unfortunately, when the secrets finally get out, you're going to have to design self-repairing circuitry. Don't ask me how you're going to do it. But remember, the job gets more challenging. That's one of the challenges you're going to see. You're going to have to design self-repairing circuitry. Fortunately, I don't have a course in that because they won't even tell me how this works. Now, I got some secrets on self-repairing from John Deere, because John Deere tractors will self-repair based on satellite instructions. So if you want to learn how to do it, I think we should really go to John Deere on tractors, because they've been doing it for 10 years longer than Boeing has. I think the agricultural people may be able to train us about what self-healing circuitry looks like from a silicon point of view. But you got to do something with those 5 billion transistors that are on a chip. And part of it is maintenance, is self-maintenance. Well, anyway, so, so that's what this dude looks like. It just completed the longest flight in history. It went from New York to Sydney, 18 hours yesterday. So if they put that into service, it'll be an 18-hour flight from New York to Sydney or Sydney to New York on the 787. Boy, 18 hours in this plane, that's grueling, okay. So what happened? This came about because these people had taken this class, I don't know, 10 years ago. And so I got a phone call from somebody in the class that said, we have this 18-layer multi-layer. We can't complete the routing. So we need to add about 300 microvias to it. I said, okay. I said, can you tell me the size of the board? Can you tell me how many parts? And can you tell me how many pins? Remember those three magic numbers? I look at my chart. I said, okay, so you should be designing an 8-layer board. How many layers have you got? They said, well, we got 18 layers. We think we're going to have to make it 20 layers to complete the design. How can it be done in 8 layers? I said, well, hire me, and I'll come down there and show you how to do it. But this should be an 8-layer board. And they say, we got an 18-layer board, and we're via starved. We have to go to microvias. Our question was, how much more will it cost? I said, well, an 18-layer microvia board is going to cost a lot more. But an 8-layer board with microvias is going to be half the price of an 18-layer through-hole. And so they debated and called me back and said, okay, yeah, we'll hire you as a consultant because, how can this be an 8-layer board? So this is what the board looked like. That's its size. It has, number one is made out of FR408, expensive low-loss material, not FR4. So we're not talking about a cheap board here. We're talking about a very high-speed board because the board works with and has optical components on it. It's the optical network controller. So it's the electronic to optical and back, redundancy control. It had 1,410 parts, 10,530 leads, 91.9 leads per square inch, 6,500 linear inches of wiring, layout efficiency at 12% or 5.7 inches per square inch per layer, and some of the design rules. That's what it looked like on a panel, 2 up on a panel with the coupons. If the coupons don't pass, the board is sent back for refund. This is mission critical kind of electronics. They're about right there, in terms of their density. This is some of the software I have that I use that tells me they're sitting right there on the line. So yeah, I know they're going to have a problem. This tells me kind of what kind of layers and thickness and things like that. But typically, I analyze the current 18-layer design to look for via starvation and interlayer routing efficiency. These are the 2 Qs originally I'd go for to see how good a job have they done. The HDI could employ via and pad, but we could also employ swing vias and look for opportunities to reduce the board size and look for opportunities to reduce signal layers by higher routing density. So they had a standard multi-layer north, south, east, west breakout pattern, kind of the standard dog bone. So I told them, well, we're not going to use a dog bone. Our top layer is going to be a ground flood. So we're not going to have vias that go to ground because ground's going to just be a bow tie-in. And layer 2 is going to be our power layer, and they're not going to be a dog bone. The micro via is going to be right adjacent to the buried via kind of thing, and they're going to be swung around like that. And so these are these big BGA devices right here. They were driving the design rule. And if this is going to be a conventional through-hole multi-layer, then it's going to be 18 to 20 layers. But if you're going to use swing vias and ground flood, it's going to be 8-layer. And so the first thing is we didn't move any part. I already figured that their part placement and layout was the best it can. So no point in moving it. But we are going to make the board smaller. So we made the board smaller, so we still have the coupon, but now in a panel we're getting 4 up instead of 2 up. Okay, so again, one of the fundamental tenets of HDI, it really helps miniaturization. So, you know, if you can move things closer together, it makes routing and a lot of other problems, but especially if you can get more up per panel, they're going to get some big cost advantages that we didn't have. And so interesting enough, our board went from there to way up there. So you can see by shrinking the board size, same parts and everything, it's even higher density. But also our efficiency numbers went up. And so the 10-layer HDI stack-up was 75 ohm and 55 ohm and 100 ohm and different busing structures and things like that, as well as FR408 material of different thicknesses, copper weight, trace width. So the stack-up kind of looked like this is another piece of my software where I can calculate impedances based on dielectric constant of the material and their thicknesses, all on one spreadsheet. It still uses polar. It just uses the polar calls, where you call the polar to do the differential or single-ended microstrip or strip line, and then bring it back to Excel spreadsheet and put it in an Excel spreadsheet. To me, I could look at the whole thing at one time. And so, you know, we ended up with a 10-layer instead of this 18-layer. The only problem is that 200 parts creeped in. The 10-layer has 1,621 parts, and what originally they gave me 1,410 parts. This one up here took 3 days to design. This thing right here, 16 weeks and not finished. And I said, wait a minute, guys, this isn't quite the same board. Where'd the 200 parts come from? They said, well, we seem to have so much room that we put the parts that we took off, we put them back on the board. What? So this is not identical. Well, no, even here, the board's not packed together. In fact, our boss looked at it and said, how come you got so much room? The original board had no room at all. And I said, well, you guys are cheating. This is not apples to apples. You now have made a more complicated board, even though it's 10-layer than we started out with. But they said, well, it doesn't matter. We're finished. 3 days and it's done. Oh, okay. So it was 35% smaller, 44% fewer layers, 33% thinner, 10% more components, 45% shorter design time, 25% cross, we actually lowered the crosstalk. We actually had space to move traces farther apart, lower the crosstalk, and still do it in 8 less layers. So their boss, they can't believe it. Wait a minute, how can you do this, but we couldn't do, I mean, it's like, what kind of magic do you do? I said, it's not magic, it's just physics, design. It's, you know, it's, and not only that, but we predicted it. This is where you were, this is what we chose, and the cost and the density is right as predicted. I told you this before we ever started, that we could do it in 8 layer, and we can. Not only can we do it in, you know, the 10 layer, but we can add 20 or 30% more components and still not have to change the stack up. And one of the reasons is that look at one of these layers. This 10 layer. For one thing, they notice that there is routing both X and Y. Yep, that's true. So how was this possible? Well, we took out 8,212 through holes that were blocking. And so over 1,000 inches on this layer, or 17.5 inches per square inch, which is 3 times what they've been getting on all their other multi-layers. And so their design manager is kind of shaking his head, saying, how can this be cheaper, work better, and be 3 times as dense? Why weren't you guys doing this last year or a year before? And they're all looking at each other and said, well, we didn't know how to do HDI. You know, we were using it, but we weren't using it very efficiently because nobody taught us how to do it. They just said, here, there's a small via, use it. So we thought it was just another via for the multilayer. We didn't realize there's a whole different design strategy that goes with it. Nobody published a book. Nobody told us. If they hadn't taken this class and called me up, they'd still be doing it the old way. Well, lo and behold, this board is finished. They populated the board. It has no EMI. They went and redesigned all 8 boards in a matter of 2 weeks. Okay? They're now looking at a $5 million bonus from Boeing for finishing early. There's no EMI. They throw away the metal card cage, use a plastic card cage because they don't need EMI connection. That saves a couple kilos, which is another $5 million bonus. So when they're all through, they got a $10 million bonus from Boeing. And nobody gave any money to the engineers and designers. The company kept it all, which I thought, that's not fair at all. The company had nothing to do with it. The engineers and designers did this. They deserved part of that bonus from Boeing, not management. You know, if management had their way, they'd still be doing the 20-layer big dude and everything. So life is not fair, just not thing, kind of thing. And so they're great friends of mine because they've been teaching other people in their company how to do HDI using my slides. So that's great, you know, you guys are becoming even more of an expert than I am, kind of thing. So example number 2 is again, an optical Ethernet, OC192, which is 10 gigabit per second. So again, this is one of those high-speed multi-layers that are difficult to design. So ask my question. It's on the other side of the line. How many parts? How many pins? What's the size? It's over the line. If you're going to do this with through-hole technology, it's going to be really, really hard. You know. And so the result of this was an 8-layer design. And you can again see a skip via, but there's my ground. Now my power is in the middle. And I've got 2 signal layers here. But that's because of the use of the skip via and things like that, via and pad. But they started out right there. We used this architecture, so there was after I finished, there was about, so the graphs that I've given you, and they're in the guideline, work pretty well about before you ever start, what are the different constructions? Is there a cost savings opportunity or not? These graphs could always be improved because this is my graph. This isn't your graph. You need to get this from your fabricator because this actually happens to be the company I started for Hewlett-Packard in Taiwan. This is their graph. And that's because these boards were actually made in Taiwan by the company that HP had me start. And they were the first to do HDI, and they do it. And they were all trained in the Hewlett-Packard PC shops. So they're really well-trained engineers, really do a good job. And they're one of the most profitable corporations in all of Asia because they know their business. The interesting thing is here's the 14 layer, and here's the resulting 8 layer. Now, those are exactly the same parts and exactly the same circuit, but somehow they don't look, the HDI one looks a lot less cluttered with the ground plane on the surface and not having to deal with the breakout methodology. The only thing that's different is, if you notice, there are 2 devices right there. There's no devices right there. If you look at the back side, there are now those 2 devices with the front tube show up there. So they moved some parts, between the 14 layer, but the 8 layer took them only 2.5 days. So to totally create this board was 2.5 days, because supposedly don't move any parts. I know some parts did get moved, but again, those are exactly the same circuits, exactly the same parts. And the general manager said, well, how much space do you have to more parts? And the engineering manager trumped up, we can stay with this 8-layer design for the next 3 years. We can continue to evolve our product, add devices, but not have to change away from the 8-layer for nearly 3 years. Over here, the reason I'm there helping them is we can't get all the parts we need on it. And now they have a 3-year, but I've forced them to go back and do a test vehicle for reliability. Because I said, again, you violated one of my rules. If you're going to do HDI, you need to create a test vehicle and do reliability testing on your fabricator and on your materials. And so they came up with a qualification plan in terms of benchmarking. And this was my second box. Take your most complex multilayer and redesign it with HDI. Because you need to learn how to make it simpler and cheaper. So instead of 14 layer, you're down to 8 layer. But the interesting thing is the reliability is going to be a 12 layer. And the reason is I want to use this methodology until 2025. So I did the calculations that said, well, by 2025, you're going to be a 12 layer with 2 buildup. Okay, so I said, okay, that's going to be the reliability. We're going to test the most complex reliability for 2025 so that we don't have to do that between now. They're only implementing 8 of these 12 layers, but they now have the plan to 2025 of how to go to 10 and how to go to 12 and how it all works. And so this test vehicle number 1 was different fine pitch part, and test vehicle number 2 was these great big telecom pin grid arrays, things like that. And this is kind of what the test vehicle looked like for the 12 layer. And so they're tickled pink because they got their roadmap planned out on how to handle increasing density, finer pitch, and fundamentally design things in 3 or 4 days instead of 6 or 8, 12 weeks. And this is a very famous telecom company that didn't mind doing it. you know, and so this is the, you know, that chart and some of their stack up and their final design and design rules. Another example is another high-speed network controller. This one is, again, involves optical networking. Seems to be a problem. And again, you can see the size of the board and the number of pins, put them on the line. If it's on the line and you're not going to use HDI, you got a 12 to 16 week job that's painful the whole way. If it's going to be an HDI board, it's going to be 1 week design time. And so this is going to be a 12 layer with only one buildup and a stack. And again, ground plane layer 1 powers layer 2. So we're back to having that very thin power ground decoupling layer. This is the component side of the original 18 layer. This is kind of the circuit side of the original 18 layer. This is what kind of looks like the through-hole part looked like from, and again, you notice that that this is kind of strange. Here, layer 2 is power. They do have power and ground. And down here, and I look at this thing and kind of scratching my head, saying, okay, that's interesting. But, you know, it's 18 layers. You know, the analysis kind of gives me how to go about it. Our result on this one is a 14 layer with SMT and ground at the top, and then power next to it, and then dual strip line in the X and Y to minimize crosstalk. But using the microvia right here to help transition that. And so the final design looks like this. And these are the actual boards. And you can see with the flood up to the surface that there's a lot of extra room on there that didn't appear to be extra room on the through-hole version. But again, they went from here up to here with only about a 16.5% savings. But the cost didn't go up. The cost went down. And that's the whole point, is that if you're going to use HDI, there's really no reason ever to pay more. If you're not saving money, you're not doing something right. Or you have a fabricator that wants to gouge you on price, kind of thing. You know, but, you know, if you're using less material with less layer and things like that, cost should go down, not up. The what? HDI, just go to the guy below you, behind you. It's his website. Oh, you found it. Oh, good.
Okay. Its section is called ebooks.
Ebooks.
Resources.com/ebooks and then the rest.
Okay, so it's there. He found it. Yeah. But don't forget, this is only 50 pages. The 007 is 860 pages. This is only 60. There's big, big difference between what's in the two books. The Interconnect 007 has reliability. It has materials. It has signal integrity. This one doesn't. You know, but this one has using Altium, and that one, the original one, doesn't. Kind of thing. So here's another one. This is another optical telecom one. It went from 22 layers through hole to a 14 layer HDI. It had about a 30% savings. You can tell the optical connectors up here coming off the board. So this kind of design metrics and alternative, my software virtually designs the entire board before I ever turn on the CAD system. So I have written very involved, elegant software simulation and modeling that allows me to to whip together a design by simulation before I ever turn on a CAD system, and allows me to optimize different design alternatives before I ever turn on a CAD system. So on my keynote talk on Wednesday, I'm going to dig Altium a little bit in that having a design planning tool is really essential nowadays. And I really encourage Altium to create a design planning tool to allow you to do what-if trade-offs before you ever get into the hardcore placement and route. Because hopefully you're walking away just saying that there are very few degrees of freedom on a multi-layer. In HDI, there's all kinds of changes in degrees of freedom. Yeah, it's complicated. How do you know which one to use? Oh, that's not a question I can easily answer, because unfortunately, you don't have my simulation software. And I can't give it to you or sell it to you, because it's unsupportable. And it's the only one in the world, and it's taken me 30 years to create. So I have to say that I do cheat. I have a simulation system that creates what I call a virtual prototype that's as good as the finished board, but I haven't even designed the board yet. And I'm probably the only one in the world that can create a virtual prototype of a finished PC board, but it's never been designed. But like I say, it's taken me 30 years to create this software. And it's not supportable because it's 55 Excel spreadsheets tied together with hyperlinks. So it's 55 separate spreadsheets for all these different dimensions: signal integrity, power integrity, cost, manufacturing, reliability. They're all separate spreadsheets, and they're all driven by macros that tie them together. So I can do a what if. What if I change this? What if it tells me the cost, and then I can, that's the optimal design. And that's what I tell people in terms of advice. So I don't know the answer until I do the simulations. I'm not that smart. I just have really, really good software that I've written. So this one was 24-layer through-hole to 12-layer HDI. And this is just a 1+. Oh, so interesting enough, so this 24-layer was HDI. They had micro vias. But they didn't use HDI the right way. They just made a more complicated, more expensive multi-layer. I ended up with a 12-layer one instead of a 24-layer one. And the kind of recent aero military boards, the old paradigm and then the new paradigm, 68% less costly, 50% thinner, and 2 weeks instead of 12 weeks. I can't talk a lot about what kind of military thing it is, but the military board designers have the same problem, that nobody's taught them or helped them figure out how to use this technology. Good. So I have a book of 50 case studies that I keep. So every consulting, every case study, I keep all the data and all the pictures and have them. I'm never going to publish it, but I have this book. So nowadays, it's easier for me to look up to a prior case study, and there's kind of the answer for this guy. People don't kind of create totally new problems. They kind of have the same set of problems over and over again. So with the examples of all the times we've done this, I can kind of find the answer over the telephone. You don't have to hire me. I can tell you what the answer is over the telephone. Well, here, try this, this, and this, and this, because I'm looking at one that actually worked just like what you're talking about, because I don't want to consult anyway or get on a plane. I'm retired. Go find somebody else, kind of thing. They said, well, there's nobody else that does this. So the sad thing is I don't have any competition. There's nobody you can hire as a consultant to help you optimize HDI. I don't know a single person in the world that competes with me. And I'm retired and leaving the business, so that's kind of sad. I need some of you guys to go into business for yourself after you've mastered all this to help other people, because I'm not going to write another book. You know, these 2 books is what you get. And there needs to be somebody that provide example and say, well, here's the old way to do it. Here's alternative 1, alternative 2, and alternative 3. You know, pick the one that best matches your need. Because guess what? We're going to SLP, and it's more complicated than HDI. If you think this HDI stuff is complicated, the SLP is even more complicated. But I'm not going to be there advising or teaching about SLP. That's somebody younger than I am to do. You know, I'm out of here. I mean, too old for this. So there is opportunity for you to master and experiment with this. One of the things to do is take your Altium Designer home and do alternative designs of your own at home, building up case studies of how you can consult or train people. Because the more work you do, the more problems you solve, not for your job, but for on your own, the more buildup of knowledge that's worth a lot of money to people that don't know how to do it. Because there's going to be more and more people that don't know how to do it, but industry demands that that it happens. Okay, come on, where's my cursor? Oh, there it is. So the last 50 minutes, since we're at 4 o'clock, is oh, wait. Okay. Is next generation interconnect technology. Where is this going? Well, obviously the SLP is one area, but an area I think that's even tougher is that we're at about the end of what we can push out of high-speed electrical nets. And we're starting to toy with optical network, so optical circuit boards. And so the next generation is very, very high-speed HDI and optical all on the same PC board. And so you're going to have to design optical circuits, which is not that difficult. So here's what the next generation. I've been doing this for now 12 years. At Hewlett-Packard, we've been in production with optical waveguides for at least 12 years. So I know all about it and how it works and things like that. But it truly is the next generation, because guess what? When you're dealing with the photon instead of the electron, you don't need any signal integrity tools because there are no magnetic fields, because there are no electrons. So the good news is, all of the stuff you learned about signal integrity, you can forget it. Because when you go into optics, you've got to worry about quantum mechanics, not signal integrity. You have a whole new set of problems, and they're in the area of quantum mechanics, which is science fiction kind of thing, Einstein theories. But there are no signal integrity. You can forget about Maxwell and Maxwell equation, because there are no magnetic fields, because there are no electrons. And it's a great fun. Also, when you talk about a net, 100 micron optical waveguide can carry 1,000 separate electrical signals. Right now, a 100 micron copper trace can only carry 2 or 3 multiplex signals, but a 100 micron optical waveguide can carry 1,000 separate electrical signals and nets. You know, so be prepared for a 1,000-fold expansion of the schematic. Because when we go to the photonic, we can carry so much more information, so much faster, because it's truly at the speed of light. So the good news is you got to have a new challenge. Hopefully they'll pay you more money. The bad news is it's a lot more complicated, not from electrical theory, but quantum mechanic theory, because now you're dealing with optical fringing, which is quantum mechanics and not. And don't ask me what an engineer called, because we don't need electrical engineers. But I'm not sure what we're going to call the engineer that's the specialist in optical circuitry. You know, believe me, right now I've worked with physicists. And you don't ever want to work with physicists because they're not engineers. So universities are going to have to educate optical engineers and not physicists, like they educate electrical engineers now. But we're not worried about electrons and Maxwell's equation. We're worried about Einstein and quantum mechanics kind of thing. So, you know, my brain hurts. It's kind of like science fiction coming true. And I have a illustration because I pestered Paramount Studios in Hollywood for a picture of Mr. Spock resequencing the circuitry in the Enterprise as little pieces of colored plexiglass. But anyway, the Enterprise in Star Trek is optical. You know, and to me, you know, science fiction becomes science reality that, yeah, in 10 years, you know, our circuit boards are going to look like science fiction things. They're going to be optical devices, just like the old Star Trek was. So it's coming true. You know, there's a limit to the electron in this magnetic field, but the optical one is wide open in terms of the next generation. You're going to have to execute it. Have fun. So why are we doing that today? Well, the first thing, the growing data of the internet. The internet is out of control. It's just going up here astronomically, and it's all because of teenagers. If people would stop sending pictures back and forth and downloading movies, it would be okay. If they simply, you know, talked. But they're shooting pictures all over, and they're shooting videos all over, and it's just cramming the internet to the point where our pipelines aren't big enough on the internet in terms of the growing data. And so there's a growing data speeds on the internet. You can see out here to 2020, you know, over here, it's all optical. The speeds that they're talking about, we just can't handle with copper wiring. We have to go to optical networking for speed and capacity. Like I said, the optical can carry 10,000 times more signals than the copper wire can. So for the space of an optical cable to replace a copper cable, we gain 1,000 more bandwidth through-hole capacity. So the economics kind of straightforward why we had to go to optical. The thing now is that how to bring optical down onto the circuit board, which is, and so here are some of the optical connections, dates, and the names of these single wavelength and wavelength division. So the wavelength division, we're learning to multiplex different laser frequencies in the same waveguide. So one of the reasons you do that is I have a 550 nanometer laser that I multiplex. I can then do a 565 nanometer laser, multiplex it in the same waveguide, then a 575 nanometer laser, and a 590 nanometer laser, and a 600 nanometer laser. So all of these lasers being coherent are different optical wavelengths. They can all run down the same 100 micron waveguide. So I can run 1,000 different laser frequencies down the same optical waveguide, which I can't do with electrons, because the electrons are all the same. But the photons are totally different. A 550 nanometer photon is different than a 600 nanometer photon, and it's different than a 700 nanometer photon. And they only interact from a quantum mechanics point of view. So I can gain 1,000-fold more communication paths in the same physical area. And the headaches, well, the quantum mechanic headaches will make your head hurt. But that's going to be the job of the next generation optical engineer, whoever that is, kind of thing. So, this is internet traffic component comparisons. Total internet traffic is just going like that. And why? It's because of Apple and Samsung. So that you heard it from me first. Within the next 5 years, Apple will take all their money and they will buy a telecom company. And you will be able to buy Apple connections to the cloud, so owned by Apple. And the reason is that Apple has all these devices, and Apple is building some of the biggest cloud computing centers in the world, but outside the United States, so not subject to US laws. And Apple won't be able to sell more devices or use the cloud unless the telecom bandwidth goes up. And the best way to do that is to make an Apple telecom company that sells you the connection. And Apple has 200 or 300 billion US dollars in cash sitting in Swiss banks. And they will use that money to buy some struggling telecom company and then re-engineer them to 5 and 6G so that your device can communicate with the cloud instantaneously, kind of thing. Because Apple is not going to be held back by the fact that we're slow to adopt 5G and 6G. They'll probably goose it along by buying their own company and making the whole thing Apple all the way through. Which means you'll be able to design your PC boards on these big, lightweight tablets, your 3D PC boards, sitting at home or anywhere you want, working on these big tablets, working off the cloud. There won't be any software in your tablet. It'll all be in the cloud. And you only rent in terms of the minutes that you use which particular software. That's really fancy and expensive, but you didn't buy it. You're just using the cloud. And so the reason this is going so fast is there's actually 4 different arenas for optical focus. There's the telecom infrastructure, how to handle all the traffic. There's a localized need for ultra-high-speed information. They want to be able to, when they're running at 3.5 gigahertz on the chip, they want the I/O to be 3.5 gigahertz, and it's not. So, they want to use optical to get the CPU speed of the chip down onto the peripheries and the I/O. The third thing is weight and power reduction, especially for automotive and aerospace. And the last one is, like I say, bringing the I/O up to the speed of the CPU. And so the demand is going like this, and the technology is going like that. There's a gap right here. And the gaps, by 2020, next year, the gap gets so big that you heard it from me first. You're using your Apple, you want to communicate with your family, and you get a busy signal. And you keep trying, and you keep getting a busy. Well, they're not using their phone. There is no bandwidth available for you to make a telephone call on. The teenagers and everybody else have totally filled up the pipeline, and you're going to have to wait until the teenagers stop messing around playing games before you can make a simple phone call. And that's when you complain to the people you're paying all this money to every month about, hey, I can't seem to make a connection. Well, the pipes aren't big enough, and it's going to be tough. It'll cost a lot of money to make those pipes bigger. And that's just the way it is. We're just selling way too many of these smartphones compared to the infrastructure that allows them to communicate. What they may do is they may start giving you a radio. And when you want to call your family, you don't use the internet, you use a radio. We go back to radio. So radio may come back, but it's your personal radio multiplexed so that you can actually make a phone call. Again, because you can't get onto the internet in order to do the digitized one. You know, it sounds funny, but so what's happening is the supercomputer. So these are what they call exascale machines, which are 10 to the 12 bits per second. Our goal right now is to have a computer that does an exascale bandwidth. And so 5 of the 10 supercomputers are IBM. And number 3 and number 8 use parallel optical interconnects, or 27 teraflops per second as of 2005. So this one right here is Mare Nostrum. It has 5,000 parallel fiber optic links at 2.5 gigabits per square inch. So they're going from 5,000 optical fiber to 5 million. The Blue Water, 2012, Blue Water has 5 million optical links in the supercomputer. 5 million. So they've taken all the copper out of it, and there's 5 million optical links in this supercomputer. And so there's some of the pictures of it. And so recently we announced several exaflop machines, and they're going to have 27 million optical links in this next generation supercomputer. The funny thing is that one of the supercomputer is, anybody here work with a Raspberry Pi? This supercomputer has 27,000 Raspberry Pi 4s in it. Each that costs only costs 30 euros each. The computer, it costs 30 euros, and there are 27,000 individual ones connected optically. That's a supercomputer. It's kind of like homebrew computers, because I have a Raspberry Pi, and the company I work, Interconnect 07, uses Raspberry Pi as a network controller. Like I say, we only pay 30 euros for those, but they're a fantastic computer. Well, somebody built a supercomputer out of 27,000 of them, which I keep envisioning this little white and red plastic box for the Raspberry Pi, but 27,000 of them, you stack them up, and you know, did they occupy this room or something? I'm not quite sure what 27,000 Raspberry Pis look like. The other big user is aerospace military. Because of weight, speed, and power improvements, the military wants, optical networking aboard, their products. And it's not just the military. The automotive guys want to use optical networking because it's not going to be affected by radar and driving past an airport. They're definitely afraid that autonomous cars and things like that, if you drive by the airport and there's radar scanning there, that you're going to affect the things in the cars. So if they go to optical networking on critical nets, that won't be affected in the cars. And then Intel itself, Intel has a piece of silicon with 1,000 individual cores operating on it, and it floats on liquid nitrogen. The only way to keep it from burning up. But all of the cores communicate with an optical layer, not an electrical layer. So they have a massive, massive supercomputer on one piece of silicon, but all the interconnects are optical. It's can't be a product because it has to float in liquid nitrogen to keep it from burning up. So they don't know how to cool it, but it does exist in silicon. And so Intel is talking about optical networking on top of the silicon instead of electrical networking. The optical is so much faster and not subject to the noise that they're going to have optical waveguides on their silicon. Which, okay, that sounds great. So one of the things I got is roadmaps. So this is an interesting roadmap to show what happened. In the 1980s, we were local long-haul wide area networks, telecom. Then in the 1990s, we were local area networks and datacom. And in 2000, we started going rack to rack and card to card. 2010, we were down to the board. 2015, we're down to the module. And by 2020, we'll be optical down to the chip. So this is how optical. This channel, oh, now it's on. Okay, great. Now I'm activated. So there's been a steady progression of optical implementation around the world. That, it hasn't popped up because it's kind of in the supercomputer area. But what are the advantages of photonics? Well, an electrical cable is the big one. The optical cable is the small. There's a 10-fold reduction in size with optical. If you have electrical connector, the optical connector is 20-fold denser than the electrical. The plug-in connectors, there's a 7-to-1 advantage. Here there's 144 12 gigabit per second mechanical connector for electrical. The optical, for the optical. The electrical one has only 21 10 gigabit per second. So there's a 7-to-1 going from electrical to optical. And then over here on the PC board, the differential pairs, you can, your differential strip lines, you can have 2 of them at 10 gigabits per second. Or in the same space, we can do 16 12 gigabit per second optical waveguides. So there's an 8-to-1 advantage on the PC board. So you can see, in every case, the optical is so much more efficient than the electrical. What we have to figure out is what the PC board looks like. So the PC board will probably not give up the electrical busing. But what we'll have is PC boards with low-speed electrical busing and high-speed optical busing. So we'll have 2 kinds of bus structures on the same PC board. The slow-speed data busing is for electrical, but the high-speed data busing is optical. And the high-speed busing will probably be CPU to CPU, core to core, memory to memory. But for a long, long time, we're going to have both electrical and optical. It will be many years before that PC board is 100% optical and there are no electrical. But there's a lot of research showing that anything we do electrically, we can do more efficient optically. In other words, I've worked on laser-based Fourier transform that was 1,000 times more efficient and faster than the world's biggest supercomputer can do analysis. In other words, the optical analysis was instantaneous versus the digital software-based for Fourier transforms. Don't ask me how that works. I haven't got the slightest idea how you do optical Fourier transforms, but it's a grad student part of the research of how to do photonic computing. Again, it's Star Trek-like stuff that it sounds like science fiction, but it's not. In the terms of material, this is an interesting, virtually 90% of all the optical materials in the world are American. If you're going to do optical waveguide, you've got to go to the Americans. There are simply very few alternatives, even here in Germany or in Japan, on efficient optical polymer waveguide materials. And here's some of the different ones. Dow Chemical, BF Goodrich, Amoco. You can see there Asahi is one of them, kind of thing. And the reason is that right now we use optical glass for long distance under the ocean, because optical glass has the lowest loss per kilometer in terms of things. But optical glass is not very efficient on a circuit board. So on the circuit board, we use polymer. And that's at about 550 nanometers. So the polymer waveguides have a lot of loss, but the distances are very short on the circuit board. For long distance, you then use optical glass for the waveguides. And so these are some of the different kinds of polymers being used. For the processes, this is fun. There are 7 different fabrication techniques of putting an optical waveguide in a printed circuit board. And there are the German technique, the European technique, the British technique, 3 or 4 American techniques, 2 different Japanese techniques, and 1 Chinese technique. You know, so I just listed all 7 manufacturing processes. I don't know which one is the most compelling. The Hewlett-Packard one is right here. So the Hewlett-Packard is probably the most fascinating because notice how fewer steps it is. Hewlett-Packard's optical waveguide started in 1995. So we started making optical multilayers in 1995 for Hewlett-Packard test equipment. Most of you have never even heard about it or don't know anything about it. You won't see optical for 5 years yet. But I've done it for 25 years. Again, the nature of HP Laboratories is to be 30 years ahead of the industry. So that's about right. It'll be 30 years between my first introduction to optical PC boards at Hewlett-Packard and when the rest of the world will see them in 2025. That's why I have all these slides. And one technique is laser ablation and laying down the optical waveguide. Another one is a PDMS molding with a mold using polydimethylsiloxane. This is the German approach at Siemens that you make waveguides. The British are doing a lot on inkjet fabrication of optical waveguides using inkjet printing at the University of Leicester. Some of the other ones in Austria are ridge formation and trench formation methods of making optical waveguide. The kind of current application, this is from 6 of my papers. So this one slide represents 6 individual papers since 1995 about optical waveguide. So I can only focus on what's happening right now. And what's happening right now is 3 separate programs. The UK program and the optical PCB, that you can see the list there, University College London and and Harriet Watts and University of Edinburgh and Wolfson School of Mechanics and Lowenbrow University, together with 8 other companies. The sponsors are BAE, Excel, Stevens Circuits, Cadence, National Physics Laboratory. So the UKOCB program is pretty well taken. You look at the universities and companies and material suppliers. So what they're looking at is an optical circuit board and an optical connector and an optical backplane for both military and telecom. And so this is what their testings look like. So they have an individual optical circuit board and a connector to plug that circuit board in and out into an optical backplane and integrated like that. For the European Union, it's University of Berlin and Dortmund and Helsinki University and Fraunhofer and IBM Zurich and Siemens and Bosch and a whole bunch of other people, German Department of Education and Research. And lead is kind of Siemens, C-Lab. And they're taking the approach of creating cavity, having optical layer, mechanically drilling a cavity, and then dropping a surface mount part that's that can be the receiver or the transmitter down into it. Most of the other ones are using mirrors to come off the surface down and mirror. This one, they're making it as a component that surface mounts into that. This is actually some of the Siemens test vehicles. This right here is optical. So these are all the separate drivers and receivers. This is an optical bus structure right there, testing for that. And you can see kind of here from the edge all the separate individual optical waveguides in this multi-layer that they're testing. And then the third one is the North America program called the Terabus Project Team, made with what I was involved with, Agilent, HP Laboratories, Avago, and DARPA, and IBM. So this is North America. So this is, over here is the current way IBM supercomputer architectures work, from the chip all the way down to the printed circuit board. And you can see right here, right now, this layer right here is the controlling area. So they want to go to an all optical one where the bandwidth doesn't have a restriction. And so, this is what the blue water, the 10,000 teraflop, is based on. They're based on Avago. This is Hewlett-Packard. Agilent is Hewlett-Packard. These are spin-off companies that HP formed. So Avago is the semiconductor part of Hewlett-Packard as a separate merchant. Agilent is the test company. Agilent has now spun off Keysight. So Agilent isn't involved anymore in electrical tests. That's Keysight. Agilent is recombinant DNA and genetic engineering. A lot more money in that kind of test equipment than there is in voltmeters and amp meters or signal network analyzers. But these Avago, these are HP products that we've used since 1995. And this is a 16 processor rack. There are 4 racks per system. And each of these guys, like I say, are supercomputers. But they're racks that slide in and out. And then the racks are connected with dual optical networking. So all of these connectors are optical networks. And they connect all of the racks, CPUs together. Again, with 5 million electrical connections, optical. 5 million optical connections, no electrical connections. All the information on and off the blade racks is optical. Within the blade, it's electrical, but off the blade, it's optical. And these are multi-layer flex circuits that are optical waveguides. And then the next generation have the waveguides actually in the printed circuit board rather than an optical cable from a Volgo. So that's called the Terabus. And there they drop in these optical chips and modules, surface mount, and within the PC board is all the optical busing, between CPU and components. So the polymer waveguide implementation within IBM along that path. And right now, the carrier, these are circuit boards right here, but this thing up here, this is a glass or a silicon PC board. So they actually have a silicon or a glass circuit board surface mount onto the PC board, for the chips. And that's because the chips are getting to so many interconnects that they have to go to glass as the interposer. So this is a PC board. This right here is a PC board. This is silicon or glass. These things up here are all silicon. And in order to get this whole thing, architecture together, and up until then, we had used the Volgo. These are surface mount parts that you can surface mount on a PC board, and they carry 12 optical channels at 10 gigabits per second, 850 nanometer. Again, using polymer, things like that. So one of the problems is how do you couple light in and out of an optical substrate? And so here's different strategies for micro lenses that are built on the silicon, things like that, or cabling on the silicon. This one idea right here is we cut holes in the PC board and we mount our parts down into the hole so they look straight into the waveguide cavity rather than using mirrors. The other techniques uses micro lenses and mirrors and kind of surface mount to get optical data in and out of the circuit board. The mirror, I like this one right here. This one right here. This is a plastic molded part that's been metallized, and there's tuning things, and a robot can come up and twist this thing and change the shape of the mirror to make sure that everything aligns, so you can have a robot align all the optical paths, from the semiconductor device into the PC board. That's pretty cute. I don't know who invented that, but this is the one that I work with. This is printed. These are computers in which, in Foxconn, we have already implemented an optical socket that you own that's not being used, but we have started integrating optical connections into the PCs that we built for HP and, well, everybody that buys their PC from Foxconn has an optical connect built in, but not being used, but it can be activated. So when the chips start taking input and output optically, the socket is already there to connect that optical today. And so, in fact, if you have an Apple Pro, you have two optical channels that you're not allowed to use or you don't know about that are physically there and can be activated remotely. So when it's time to buy Apple connectivity, you get a cable and all of a sudden magically your Apple Pro will communicate optically and not digitally. But it already is existing in the product, not being used. Apple has an optical channel. That's one of the funny connectors that you always wonder, what's this connector for that I don't seem to use? Well, that's the optical connector that will be used in the future once we sort out how we're going to do all this bandwidth business. with that, we have time for question and answers because the cocktail hour doesn't start until 6 o'clock. So with that, I know that's a lot, but I'll kind of throw it open for areas that we should go back to or questions you might have. Yeah. I wish the only way we had was trial and error. So we built the layer pair. We left all the decoupling capacitor. We turned it on. We looked at our network VNA, and we started looking at the impedance, the high frequency impedance of the power distribution network, all the peaks, and we started unsoldering decoupling caps. And every time we would unsolder a decoupling cap, it would go down or a peak would go down. So we kept taking them off until it went up. And then we put that cap back on. And we kept taking these things away until anytime we took away any more caps, the performance got worse. It never got better. And typically, we were left with 10 to 14% of the decoupling caps. So what we started with, we removed 86%. And this seemed to work over and over, no matter what the voltage was. As you notice that the 1200 microfarad, the power capacitor never got removed. Couldn't take that guy off. Everything went to hell. Okay, put him back on. But all of the other decoupling caps, 80% of them, 85% came off for the best performance. So it was never 100%. You have to have some. We did find out, though, that we took this off, it got worse. We put it back up here, it went back to being good. So it's no longer critical where it's at. That putting them into a matrix was far superior than putting them near the components. So one of the things was moving the decoupling caps out of the critical area seemed to help. You have to have them, but they don't have to be. Why? Well, because the impedance is near zero. We're at 0.1 or 0.01 ohms. And so it doesn't have to be right there. It's just as effective as up there. And so I don't know if anybody's doing research or providing design guidelines. I haven't seen anything that talks about the optimal use of distributed capacitance. But there's a lot to be learned there. You just have to do it through experimentation. Because I don't know any modeling tool that told us which decoupling caps we don't need. We had to put them all on and then individually take them off before we found the optimal performance.
There is no need for them to be underneath the VGAs?
No. With a really low power distribution network impedance, they do not have to be next to the BGA. They have to be there, but they can be spread out uniformly. They don't have to be right there. And that's great because they're always in the way. Got to put them in, but they're always in the way. Now they don't have to be in the way. And you only need 10% of what you're used to, or 12% of what you used to put on. But again, I don't know when signal integrity modeling tools can tell you all this beforehand. Like I say, ours was trial and error to figure it out.
Were you doing that with the fully loaded or stressed PCB with the fully capabilities? Or what I say?
Say it again.
Did you overload the PCB and then make measurements?
No, what we did is we designed the conventional PCB with the conventional decoupling cap rules. But the power and ground was, the highly coupled thin dielectric power and ground instead of power and ground being separate. So we were using buried capacitance or distributed capacitance. Okay, what we found out was it wasn't better, it was worse. And so that's when we found, we've got to take away the two capacitance are fighting each other. They're forming resonant circuits that are causing all kinds of noise. So if you take off the decoupling caps, you're removing L and C, and peaks keep dropping and going away. So they go away. So we kept taking them off until it didn't get any better. And then once it didn't get any better, we started moving them around and it got better. And the resulting was we only had 10 to 14% of the decoupling caps left to get the best performance. But more capacitance is not better. If you're going to use distributed power and ground pairs for low impedance, you're going to have to remove the decoupling caps, or it's not better, it's worse. And a lot of people never told us that there was a negative side of using buried capacitance. And the negative side is these decoupling caps and their inductance and capacitance interfering with the planar circuitry. I have never ever seen that in printing or as an advice anywhere. Yeah, but that's what happened when we started using these buried capacitance. But that's good news, because we just as soon get rid of 80% of the coupling caps on the board. That's a big improvement. Frees up real estate. And yet, like you see, we finally got down to very, very low power distribution network impedances. And with low impedances, we have much more freedom on routing and return paths, because now our return path could flip between power and ground. In other words, our return path is not a single plane of copper. Because the impedance is nearly zero, the return path jumps to find the lowest inductive path back to the source. And so it makes for much high. It's obviously a very important design consideration in 5G on very, very high speed. How these signals are going to get routed. Because I'm not sure anybody's putting out any instructions on how to design 5G boards. Going to be kind of trial and error with new materials, obviously. Yeah. And the new materials may be these thermoplastics, not the thermosets. Certainly not going to be FR4 kind of thing. Anything else from this morning, this afternoon? Like I said, I'm here through Wednesday night, but yeah.
About those coupons which you mentioned.
Oh.
Putting on the tooling rails.
Yeah.
You are making the test for each batch or for each board?
No. Of our 60 million boards a year, every single rail, our boards are in rails. Every single board and every single rail for those 60 million boards have traceable coupons on them back to the qualification. So if Toyota says this electronic's not working, give us the code, we can go to our warehouse, open a drawer, and there's the rail of the fabricator rail of when we assembled those PC boards. We can pick up that rail and go back to the laboratory with coupons of what Toyota just reported might have been a failure, field failure. But 100% coverage of all 60 million boards. Because with automotive electronics, Bosch and Toyota, that's what they insist on, is quality, quality, and quality, reliability, reliability, and reliability. They are 100 times more difficult than military, 100 times tougher, than the military ever was, because it means money to them. They don't want failure under warranty, And so one of the questions I asked to my boss was, what's the design life of our electronics? And so they told me 15 years. Warranty life is 6 years. Our company designed 15 years. Okay, can I look at the reliability data that supports the 15 years? They said, we don't have any. Well, wait a minute. How can you say that it's 15 years? Well, that's because what the engineers tell us. I said, what do you mean? I said, where's the data? We don't have any data. And I said, that's no way to run a company. You know, if you're telling BMW and Mercedes and Audi that our life is 15 years, you should have some proof that it is 15 years. And the CEO said, well, you're right. I said, can I undertake a program to determine the operating life of our equipment and our designs? And he said, yes. So you saw some of the data. So I went off and started testing all of our laminates, all of our fabricators, all of our design rules, all of our assembly processes to whether or not they had a 15-year operating life. And they didn't. So I made changes and retested again to, in fact, our equipment will last 15 years in the field, and we have the data to prove it, kind of thing. Because it's nice to say, oh, we designed for 15-year life. What was he talking? He was talking about the semiconductor. I said, wait a minute, you know, that's great that the semiconductor will last 15 years, but our product has got circuit boards and cables and connectors. When I say 15 years, the whole thing, because I asked him, what's the aftermarket non-warranty replacement cost for our anti-collision system? It's $1,700. I said, we're going to have an awful lot of pissed off car users if their anti-collision system fails and it's not under warranty. Because for them to replace is $1,700. That's our fault, not theirs. And he said, you're right. If we say it's 15 years, it lives to the warranty life plus 2 plus 3 before it possibly can fail. Because there's no way to keep customers having them buy, especially an anti-collision. You don't, if you're going to buy anti-collision, you want the anti-collision to work. And if it fails, but you're not under warranty, you're going to have to pay big bucks. Not if it's our company's anti-collision system. Because I got involved and said, we can't be in business saying 15 years if we haven't really tested our stuff to 15 or 20 years to make sure. And guess what? We eliminated some fabricators and we eliminated some materials that would not last 15 years. But we found fabricators and materials that would last 20 years. And so they build all of our product. Not a single of our product is allowed to be built in China. We have no components and no materials from China ever. Because they simply, their stuff will only last 3 or 4 years, unsuitable for automotive electronics. But we get a lot from Asia, but it's not allowed to be from China. And we buy more expensive materials. We don't buy cheap materials, because cheap materials aren't going to last 20 years in an automobile. When some of the automobiles are up in Alaska, and it's really cold at night, or some of the automobiles are in Phoenix, Arizona, the desert, and they park it in the sunlight, and the electronics goes to 220 Celsius, you know, day after day. That's because our electronics, especially our anti-collision, sits in the windshield behind the mirror, so it has the broadest view. So it's in direct sunlight all the time. And you can't guarantee that people are going to park in a garage, you know, like in Arizona, or they're going to be parked in a heating system in Alaska or Oulu, Finland. You got to test for those extremes. And a lot of materials simply not good enough. That you would use for a personal computer or for a mobile phone, not good enough for automotive electronic reliability. I don't know what the military uses, but I know that our specs from Toyota are stiffer than any military specs when it comes to reliability. You want to read good reliability specs, read Bosch or Siemens or Audi, BMW, their specs, or Toyota. Kind of, those are well-written, difficult specifications. Because they can't have cars failing under warranty. Now, unfortunately, they don't care too much if it fails when it's out of warranty. But that concerns me, because I typically keep a car for 10 to 12 years. So, you know, more than half of its life is going to be out of warranty. I don't want to have expensive repair bills. I want the car to be built out of components that will last 15 to 20 years, you know, and not personally have to pay, you know, the bill kind of thing. But we had 95% world market share. So every vehicle in the entire world always buys from the company I work for. We had no competitors anywhere. Well, down the street was a competitor that had 5% market share. But between the two of us in the same town, 100% of the anti-collision electronics used around the world, kind of thing. And our business was growing at 15 to 20% every year, and on this really fancy, you know, because we added LiDAR, laser radar, to our conventional gigahertz radar, and our two side mirrors have radar, and they wirelessly communicate with our central processing unit. So there's more computation going on in our anti-collision, because we can identify animals and things like that from humans, and we can even put a picture of them on the rear view mirror. We can actually show a picture of the animal that you're going to hit if you don't stop or something like that. And we can differentiate. We can't differentiate a little squirrel, so just run it over. But if it's anything bigger than a badger or a beaver, we can see it on our LiDAR radar. You don't want to hit a badger or a beaver. They can cause some real damage. You know, the animal's got to be this big and easy to crush. If it's too big and too strong, you know, and of course, if it's an elk or antelope or a deer or a moose, it gets bigger and bigger and bigger. It's really disastrous. You don't ever want to hit a moose. They weigh over 1,000 kilos, and they're big and muscular. They have a tendency to kind of crush the entire front end of the car as they go flying that way. They're dead, of course, but you know, your car is crushed. But for a little squirrel, afraid our systems don't detect them, you just run them over. What was that? That was Rocky. Just got run over, kind of thing. Now, and I don't know, we have a lot of animals in North America. I mean, on four legs running around. I don't know how many animals you have here, but we got a lot of them in North America, especially where I live, because I live in the forest, and there's lots of animals, kind of, you know, just everywhere. It's fun going to Australia, where they have virtually no animals running around except a kangaroo, and it's going to get two legs. Everything flies in Australia, but there's very few things on the ground. Because I started reeling off all the four-legged creatures we have. You know, the Australians, we don't have any of them. None. Oh, that's interesting. But they got all the poisonous snakes, so, you know, they can have the poisonous snakes. I'll take the four-legged animals, kind of thing. So, anything else? Like I said, ask that gentleman over here how you find this. The PC handbook I don't have because it's so big, I don't carry it with me, but it's easy to find an iConnect 007. When you're on the iConnect 007, you can also register for the free magazines each month on design or fabrication or assembly. Or there are 20 books on technology you can download for free. So if you're interested in a particular subject in electronics and design, there are 20 separate books there, textbooks, that you can download for free.